Next, I would like to welcome Dr. David Kazdan, Alpha Delta 8 Yankee, to the podium, along with students Aiden Montare, KB3 UMD, Skylar Danhoff, KD9 JPX, and the last co-author is John Gibbons, N8 OBJ, and the Whole Case Amateur Radio Club, W8 EDU. Thank you.
Thank you. I've got a lot of duplicated material here from the last two talks, but we're split into three parts. I get 5 minutes, these two get 5 minutes, and our technical advisor, John Gibbons, is going to take a few. We thank the Case Amateur Radio Club, a word from our sponsors. We're addressing largely the same problems that have been discussed here. The short version of it is Nathaniel, as opposed to all the other Nathaniels here, this Nathaniel needs data. And the data have to do with measurements of the ionosphere, with atmospheric effects on the ionosphere, with the bow wake of the moon from the solar eclipse, which had been predicted and was joyously actually detected and documented. I've already lost where Phil is. You're back here someplace. Well, by Phil and his crew from MIT. And HF Doppler provides a surrogate measure of direct ionospheric effects. There are rocket ionosons that are sent up once in a blue moon when there's money and political will and all the other things that requires to do an ice pick measurement of the ionosphere. But having a continuous distributed measure is something different. It's got to be done by a surrogate measure, and perhaps shortwave radio provides it. As Phil said, we're already paying good money for these beacons. WWV was slated to be defunded. The director of NIST, I'm half ashamed to say, is a Case alumnus. And he slated WWV for defunding. They're still on the chopping block for the end of September, one day before their 100th anniversary. So we'll talk about that a little bit. Why do we do this at all? Because the predecessor of the FCC gave amateur radio 200 meters on down, and it was the amateur radio operators who discovered SCIP. The SCIP is largely as discussed here. I really like this slide that has the NASA logo on it, that talks about the various kinds of SCIP, has nice little pictures of the space station and the space shuttle. But actually, you may not be able to see it. This neatly weaves in 4 kooky NASA fantasies. This slide is from a skeptic's website. And in particular, the last one here, that the higher frequency radio waves pass through the ionosphere. This is the big lie that props up the satellite hoax. Isn't that great? Okay, slide. NIST is your tax dollars at work. You can buy the most expensive peanut butter on earth from them, but they did provide the new standard for the kilogram along with the rest of the international physics community. Slide. And this is their antenna farm. The heartbeat of shortwave radio. Note that the 100th anniversary, once again, is October. Please, everyone, say nice things and try to be involved in what's going to be the biggest nerd party ever. The 5-day, 24-hour-a-day special event station of WW0, WWV, on their 15 acres outside the security fence. We are involved in planning some parts of it, and yes, it's going to be great fun. Be there or be part of the Purcell equation. Slide. Do not forget our northern friends. CHU Canada is the Canadian National Physics Laboratory, and their beacon monitoring during the eclipse is also going to be of interest. The path of the 2024 eclipse is quite different from the 2017 one, and we're going to be in totality here. We paid really quite well for Case to be in totality and MIT not to be. Yeah, and the exact path means that beaconing across CHU and across WWV's side mirror image of the path is going to be quite important. Slide. Also, the frequency measuring test. You want a good warm-up for this. This is the Periodic Nerd Festival. I won't say too much about it, but Thursday evening, local time, the day before that UTC date. Thursday evening, April 11th, 10 o'clock Eastern time. Let's all do this. It's fun. Slide. All right. WWV is out there. It's almost as if it were a natural resource. This is the longest running radio station in the world. But ionosphere measurements also started radar. From the 1920s, this is from the 1930s, there were ice pick pulsed radar systems going straight up. I'm looking for some confirmation from somebody who actually knows what he's talking about. Going straight up into the ionosphere here at Beltsville, Maryland, looking for time-of-flight signals and detecting the lowest layer of the ionosphere, higher layers, yet higher layers in a sweep of frequency. This is still going on in several places on Earth every 15 minutes, data recorded every hour. So the ionosphere got discovered early. It was hypothesized remarkably early, but it got discovered and verified early. Slide. So SCIP is a long identified phenomena. It's important to all of us. And this was going to be, the expectation in the late 20s, early 30s was this was going to be commercially important because it would verify the availability of long-distance radio paths, Skip. But again, WWV is this odd pseudo-natural resource. As far as I can tell, John Krause at Ohio State was the first one to make use of it as a scientific instrument for its signal. He was a very involved ham radio operator from the 30s. He knew about meteor scatter and managed to use the theory of meteor scatter to identify Sputnik's breakup in the atmosphere as it re-entered. It's a fascinating story. Slide. So what has changed since Krause's time? That was an amplitude measurement. What's changed is that not only can WWV have extraordinarily high precision at taxpayer expense, you know, we all chip in for that one, but we get it too locally. Cheap GPS oscillators. Slide. So our task is to use cheap equipment that we can distribute. Slide. Nothing fancy here. This is just a single stage mixer. Slide. And use readily available, easily understood software to do the frequency estimation and recording in a standard format that can be uploaded. Slide. For all of our purposes. We're in preliminary stages here, but this will give you an idea what we're recording. This extraordinary Doppler shift at dawn here, this represents at least a couple hundred kilometers per minute of change in the path length of WWV. And what we'll next hear about is how interestingly this changes over time. So, finish up my slide. Yes.
All right, thanks David for that introduction to what we've got going on here. So we've been monitoring WWV on 5 megahertz and 10 megahertz. Oh, sorry. David had one more slide, but all right. First, I want to preface this data with this is the scripting genius of Aiden right here. He's the one that's been processing all these plots. So thank you, Aiden, for your fantastic abilities in that sense. Oh, all right, thank you. All right. So what we've got here, this is 10 megahertz from WWV. This is a filtered plot of our discrepancy that we're seeing between their transmitted signal and our received signal. And so already we can see, as Steve Kerwin was already observing with his data, these Doppler shifts at specifically sunrise and sunset. So we can see that as the ionosphere strengthens and lowers in sunrise, our path length is going to be decreasing for our for the wave that we're receiving, and therefore we'll have that shift. And likewise at sunset, as the ionosphere rises back up, that Doppler shift will also occur in the opposite direction. So like I mentioned, we've been looking at both 10 megahertz and 5 megahertz. It's kind of interesting to look at the difference between the two signals. Because we know that the 10 megahertz signal is going to bounce at a higher altitude, and the 5 megahertz signal could be bouncing at a lower altitude. It's kind of interesting to note what's going on between the two altitudes, and perhaps different patterns and different ionospheric effects that are happening at the different levels.
So one thing that we were actually theorizing and we've been talking with Nathaniel about is that we think that the data during the nighttime, which is on this side of the plot, shows evidence of some traveling ionospheric disturbances. So these are disturbances in the ionosphere that travel positionally above the Earth rather than rising or falling. And so we've got, it looks like there's more periodic components in this part. It sort of looks like we've got longer components, just roughly maybe like about 2 hours, and then something on the order of 15 to 30 minutes. And we don't see the same during the daytime. So one future direction is we want to look to see what kind of, we want to see if we can correlate these with other measurements to record if these actually are ionospheric disturbances. So a lot of our plots that we've generated so far look like the typical plot. This is the one we just showed in the beginning. But we've also got a lot of other interesting stuff in the data that we'd like to explore further. This happened during the night. Not really sure what that is. So we'd like to try to correlate that with space weather observations. That's something we're looking to work on. And now we're going to welcome up John. And what John has been doing is something rather interesting. He's been using his home SDR to record 4 different frequencies of WWV at the same time. And so this is actually from this week. This is the past couple days, and you're seeing sunrise and sunset and all those frequencies at once. This part is a little bit of an error, we think, but we're looking to see if we can compare the responses of the different bands.
Yeah. See if we can get this to work here. Question.
Unmute this one, or no?
Okay, my name is John Gibbons, call signs N8OBJ. I was licensed in 1991. First off, this is coming from a Flex 6500, which I purchased at Dayton several years back. And it is a SDR that is sampling basically at the antenna input at 246 megahertz at a 16-bit depth, and those are engineering bits, not marketing bits. Yes, I've been, just as background, I've been in the industry for 35 years. I spent 20 years at Keithley, and my specialty is analog design, and my specialty at Keithley was doing the electrometer design. So if you've ever seen a 6517B, that's my little baby. Anyway, getting back to this, I was monitoring this. I started this up on Monday evening for David, and being that I could look at 4 slices of the spectrum simultaneously, I looked at 2.5, 5, 10, and 15 megahertz, which you see here. That is the raw data. That is the filtered data. And you can see there's a pretty good correlation, as you would expect, and not a really big difference between the 4 bands, which I found kind of interesting. But this, like I say, you're seeing this pretty much at the same time I'm seeing this. This is what the SDR looked like during the capture. This is in an evening time slot. The UTC, you can't quite make it out. It's about 2 a.m. UTC time. The top slice is 2.5. Actually, I got the technology here. This is 2.5, this is 5, this is 10, and this is 15. You'll notice that right around here, there's a real small window there, and I actually put a band pass filter there that was plus or minus 20 hertz. And it has 65 dB per decade roll-off walls. So basically, I was looking at 40 hertz around each carrier frequency, and what I did is I set it to upper sideband and did an offset of 1 megahertz, or 1 kilohertz, so I'm looking at a 1 kilohertz upper sideband signal, which is the carrier. And then I basically fed that into FL-Digi, and using the command line interface, I got Windows 10 to run 4 instances of FL-Digi simultaneously, and was doing the frequency analysis. You can't quite make it out, but these are typically within a tenth of a hertz. Now, the frequency reference for my Flex 6500 is one of the Leo Bodnar discipline oscillators, so it's within millihertz of the correct frequency. So, getting back to that's sort of the tail end of the other part, and I see the yellow light turn yellow, so I'm in trouble already. I was monitoring from a very, very long time back. When I first took my ham exam, I was trying to figure out, when I was studying for it, how on earth would you monitor propagation? It just seems like very expensive, because you'd have to have a transmitter going 24/7, and who on earth could possibly provide that? And then it dawned on me, wait a minute, WWV's doing that. So what I had back then, as you can see here, keep losing my pointer. This is the Heathkit most accurate clock. So I designed a interface using a prototype, which I'll explain at a little later date and time, which has a very interesting story, which is actually turned out to be the funding for ThinkBox, but we won't get into that yet. But basically, I look at the high-spec light, which is when it determines it's captured the signal. Now, what this does is it looks at the 5, 10, and 15 megahertz frequencies. It looks at, and jumps on about a 3-second rotation. It looks for the 100 hertz data. There's a 100 hertz phase lock loop inside this thing. If it's seeing the 100 hertz data, it then tries and see if it can find the 1 kilohertz data, which is the capture light, which lights at the top of the minute. If it gets several minutes of, actually 3 minutes of consecutive correct decode, it then kicks on the high spec light and locks onto that channel. And what I do is when I see the high spec light on, I kick the clock and I grab the time. And then I keep going on, and when it drops out of spec, high spec, and when it loses it, I kick it again and grab the time. So what I've actually accumulated over the last 28 years is capture times for 5 megahertz, 10 megahertz, and 15 megahertz for WWV. I have them in individual frequencies, and I also have a composite graph. I also have the statistics for the year, and I also have the raw data. This is all available on my website, which is simply naobj.com. But we get into, that's what the statistics typically look like. This was a particularly good year, 1999. I had 2,079 sync-ups of the clock during the year. And as a reference for 2018, I only had 612. As you can tell, there's something going on there. This is what the raw data out from the clock looks like. Actually, from the monitor I wrote, it's a Z80 written in assembly language. And this is how I kick this stuff out. So I get the band information, the time of when it's synced up, and the time when it dropped out. Now you'll notice that it's always at 59.0 when it syncs up. That's just the way the firmware in the Heathkit clock works. And this is basically what we're trying to figure out how it works. These are the sun cycles since I started in 1991 was here. So I've been through a couple cycles. And as I'm going along, I'm going to show you, and I labeled what's going on. This is the composite graph of 1991 when I started. Roughly, I got the firmware, everything working mid-September. The blue plots are 15 megahertz sync-up times. The green plots are 10 megahertz, and the red ones are 5 megahertz. Now put on your seatbelts. We're going to be moving quick here because I got 28 years worth of data to show you. Okay, there's 1992, 93, 94. It's an interesting anomaly that I'll get back to later on that one. 95, 96, 97. We are now at the end of cycle 22 of the sun cycle. So we're at the minimum there. There's 98, 99. And I should point out that this is 0 hours UTC, this is noon, and this is midnight. So as time marches on, you go up, and it wraps around for the next day. So as you can tell, the 15 megahertz band is pretty much active during the daytime hours. And as you go farther along, you'll find that the 10 megahertz band tends to be active at sunrise and sunset, and the 5 megahertz band is predominantly active at night. So there's 2000. Okay, sun cycle 23's peak. You'll notice that lots of 15 megahertz, lots of 10 megahertz, and sprinkle in there very little, usually some 5 megahertz. Now the limitation, red light. Limitation of this radio receiving technique is when I'm locked onto one frequency band, I'm ignoring the other two. So that's a limitation, but in 1991, that's all I had. We didn't have SDRs back then. There's 2002, 2003, 2004. One thing I want to point out, on the 15 megahertz band in the summer, typically there's a hole there. It fades out during the summer, and it's more popular, or much more strong in the winter, and you'll see that as a recurring theme. 2005, 2006, 2007 data was eaten by Windows XP. At that point in time, I quit Windows and started using Linux. That was January 2nd, 2007. And I haven't looked back since. 2008, 2009. Now you notice this is becoming very, very active. And we're at the end of the sun cycle there, which is very interesting. But you'll see 10 megahertz, you'll see it showing up. This is basically sunrise between, I'm guessing, between Fort Collins and Cleveland, or at one of the hops. This stays pretty consistent, but in some of the data, which I'll jump back to, it actually, with the summer and the Earth rotating for the, on its axis for the summer, that the nighttime one shifts with that. There's 2010. Notice 5 megahertz is very predominant. 10 megahertz is very, very little. 15, again, disappears in the summer, active in the winter and fall. 2011, 2012, 13, 14. We're at the bottom of sun cycle peak 24. I'm sorry, we're at the top of sun cycle peak 24. 2015, 2016, 2017. There's 2018. 2018, we got 1, 2, 3, 4, 5, 6 sync-ups during the entire year on the 10 megahertz band. Now, one thing I want to point out that happened in my 28-year data collection. On May 5th, 1994, at 7:18 in the evening, 15 megahertz band synced up. It did not drop out for another 4 days. It was solid for 100 hours and 4 minutes, which looked like this little thing right here. I suspect there was some sunspot activity at the time that caused that, but that's for Nathaniel to figure out. Any questions? Thank you for your time.
Okay, I think in fact we probably used up our question time. But that is really fascinating. That's an extraordinary data set. And once again, we have the last natural RF fountain in North America in the form of WWV. Preserve it. A quick question.
At this point, no, I haven't had a chance. I was planning on trying to plot a lot of that stuff relative to the sun cycles and sun, but right. And this is sort of a very simplistic way of monitoring it, but like I say, I've been doing it for 28 years, and you can sort of see as things fade, and something has changed because in the last 4 years, I'm getting a lot less sync-ups. I was typically averaging between 16 and 1,800 per year. The last couple of years, I've only had like 600 or 700, so something is changing.
Okay, let's defer